Okay, everyone, welcome back to part 2 of the CSEC chemistry specimen paper. So we're working through that paper 1 that CXE provided from June 2012, and we're just working our way through to get some practice for the upcoming paper 1 exam, right? So now we're at question 31, and 31 says, which of the following quantities of acid can exactly neutralize 40 cm cubed of 2 mole per dm cube sodium hydroxide, right? So we know that this is going to be an acid-base neutralization, right? So we have an acid that's reacting with a base to give us salt and water, right? So the acid plus the base is going to give us salt and water, right? So we can come up with equations that would represent the acid reacting with the base, right? And so that's really, I think, where we want to start in this kind of analysis. So they say, which of the following quantities of acid will exactly neutralize the base? Well, let's write the equation for HCl reacting with sodium hydroxide. So sodium hydroxide and HCl react together in a 1-to-1 mole ratio to form sodium chloride and water, right? Sodium hydroxide and sulfuric acid now are going to react in a 2-to-1 mole ratio to form sodium sulfate salt and water. And then sodium hydroxide and nitric acid, right, are going to react in a 1-to-1 ratio to produce sodium nitrate and water, right? So this is like our first step, really, is this step here. This step here of writing the balance reactions that we would expect to happen in those instances and then come out with our mole ratio, right? Now, once we get our mole ratios, what we have to do is say, okay, how many moles of sodium hydroxide do I have, right? And they told us, they gave us the volume of sodium hydroxide that we're going to try to be neutralizing with the acid. They gave us the volume and they gave us the concentration of that sodium hydroxide, right? So if we want to find moles, we know that moles is equal to concentration times volume. And we know the concentration of that sodium hydroxide is 2 mole per dm cubed. And the volume is 0.040 dm cubed, right? I converted that 40 cm cubed to dm cubed. And so when I multiply those two through, I'm going to come up with 0.080 moles of NaOH. That's how much I'm trying to neutralize with my acid. Any one of these acids, right? All right. So let's see. If we said that the molar ratio of sodium hydroxide to HCl is 1-to-1, then if I have 0.080 moles of sodium hydroxide, what's going to exactly neutralize that will be the 0.080 moles of HCl because it's 1-to-1. So then the task is to find out how many moles of HCl is this, right? And when we calculate that through by multiplying the concentration times the volume, we find out that this is 0.020 moles of HCl. And that's not enough, guys, right? Remember, it's 1-to-1. So if this is 0.080 moles of NaOH, we need that exact same amount to be present in HCl. And so because that's not what we got, this won't work, right? That won't exactly neutralize our sodium hydroxide. So now the second one, now let's look at how many moles of sulfuric acid we have. We know that sodium hydroxide and sulfuric acid react in a 2-to-1 mole ratio. So if we have at least half of this moles, this number of moles in sulfuric acid, then we'll be good, right? So let's see how many moles we have. When we do concentration times volume, we end up with 0.040 moles of sulfuric acid. And that works, that can work, because we have 0.080 moles of NaOH, and we need half of this in sulfuric acid for it to work. So this might work, right, to exactly neutralize our sodium hydroxide. So then for the third one now, how many moles of nitric acid do we have? We have 0.080 moles, and that's the exact same amount of NaOH that we have. And from our balance reaction, we know that we need them in a 1-to-1 mole ratio, so we're good where nitric acid is concerned. So this could neutralize our NaOH, right? So then our final answers then now are going to be that 2 and 3 could exactly neutralize the NaOH, right? So that would be D. Okay, guys, our answer for this one is D. So 31 is really a combination of acid-base titrations and knowing how that works, and then also knowing your mole concept, okay? So to be able to insert that in here to do this calculation. All right, so moving along to question 32 now. So 32 says that Epsom salts or magnesium sulfate, that's the scientific name for it, is widely used, right? Which of the following statements are true of this salt? So Epsom salts relax the muscles, that's true, right? It sedates the nervous system, so people will use it when they want to calm down a little bit. They might soak their feet in it, or they soak themselves in an Epsom salt bath, right? So it sedates the nervous system, that's correct. It is also used as a supplement for plant growth. This is correct. And what it really leverages here is osmosis, right? And that whole idea of osmosis and with being able to withdraw water so that slugs can't live on the plant, okay? So that's what's at play for the third one. So all three of these uses are accurate. These statements are all true of Epsom salt. So that's D. Okay, so these are answer for 32. 33 now says, which of the following acids is important for healing wounds? So what do we use for wound healing? Lactic acid? No, that's not what we use. We actually use ascorbic acid. So our answer for 33 is B. And ascorbic acid is an antioxidant, right? So that's vitamin C, guys. It's an antioxidant. That's ascorbic acid. And what else do we know about ascorbic acid? Ascorbic acid is also it's used to promote healthy connective tissues, right? So healthy connective tissues in the body. So that's very good for wound healing, right? Healthy connective tissues in body. Healthy connective tissues in our body. So those are some uses of ascorbic acid, okay? All right, so that's where we are. So 33 is B. Ascorbic acid is helpful in wound healing, okay? So let's go on to 34 now. 34, so which of the following classifications is correct? All right, so we have a column that's basic oxide, and we have acidic oxide, and we have neutral oxide, right? So sodium, so the oxides of metals are generally basic oxides. So this is correct and this is correct. And then also copper 2 oxide would be correct. It's in the right column, right? They're all basic oxides because they're oxides of metals, right? Let's see. So sulfur 4 oxide wouldn't be a basic oxide. It would actually be an acidic oxide. So this is wrong. That's in the wrong column. So we can strike out that one. Strike out C. That's not going to be correct because this one is wrong. Aluminium oxide now. Aluminium oxide is a neutral oxide. So that's in the wrong column. Water is neutral, of course. So that's in the right column. But we can strike out A because if one is wrong, the whole thing is going to be wrong. Okay? Now let's look at carbon dioxide. Carbon dioxide is an acidic oxide. That's true. But sulfur dioxide, as we said, is an acidic oxide. So this is in the wrong. This is under the wrong title. And so we can strike out B as well. So that leaves us with D, guys. So these are answer for 34. Okay? So copper 2 oxide is a basic oxide, carbon dioxide is an acidic oxide, and carbon monoxide is a neutral oxide. So all of these are correct. And so, yeah, these are answer, okay? Calcium oxide, as we say, is an oxide of a metal, so this would have been basic, so that's not right. Carbon monoxide is neutral, so that part is right. But the only one where all three are correctly assigned is D. So these are answer here, okay? All right, so moving down to 35 now. Items 35 to 38 refer to the following options, right? So option A is propene, option B is methane, option C is bitumen, and D is medicinal paraffin. Okay? So they're asking us to match each item below with one of the options above. So we're matching these items with the options above, and they say each may be used once, more than once, or not at all, right? Okay, so 35 is saying which of these is a major constituent of natural gas, and that's methane, right? So 35 is B. Methane is a major constituent of natural gas. Which of these is the residue in the fractional distillation of petroleum? So our residue is going to be bitumen, right? So that's C. So 36 is C. Which one of these requires the least oxygen per mole for complete combustion? Least oxygen per mole is gonna be methane again, right? So 37 is B. We don't need a lot of oxygen to completely combust that methane, right? Because as the formula would be what? CH4, right? Whereas propene would be what? Propene is C3H6, right? Because that's an alkene. So we would need less oxygen per mole of this to completely combust it than we would for this, right? So methane is our answer for B. So 37 is B. And then 38 now. Which one of these is used in making plastics? So remember, the way that we make plastics is through addition polymerization. And for addition polymerization, we need an alkene. So our alkene here is propene. So our answer for 38 is going to be A. Okay? All right. So looking at 39 now. 39 says an organic compound X has relative molecular mass between 40 and 50. When we shake that organic compound with bromine, the mixture quickly turns colorless. From this information, what could X be? Right? So they're giving us all these options here. This one is ethene, this one is propene, this one is ethanoic acid, so that's a carboxylic acid, and then this one is ethanol, right? So which of these could X be? So here's how we're going to break this one down now. So our organic compound is X, right? It has relative molecular mass between 40 and 50 is what they told us, right? When we react that organic compound with bromine, the bromine is going to go from orange to colorless. So that indicates that there's an alkene of some sort present, because remember, alkenes are the compounds that can decolorize bromine, and that's because they have a carbon-carbon double bond present in them. This doesn't have a carbon-carbon double bond. This doesn't, but these two do. So the answer is between these two, right? These are both alkenes, so we have to choose between these two because they both would decolorize bromine, right? Because they both have double bonds. But the difference between them is the mass, right? They told us that the relative molecular mass has to be between 40 and 50. And for ethene, so this first one, the molecular mass there's going to be what? 12 times 2, 24 plus 4. So the RMM is going to be 28 for this one. Whereas for this one, it's going to be 36 plus 6, so that's 42, right? So our answer is going to be B. So we've met all our criteria of it being an alkene because it decolorized bromine, and also that it had an RMM between 40 and 50. So that's B, okay? So our answer for 39 is B. We are moving along to 40. So 40 says that ethanol may be used as a fuel because it is easily converted to ethane. That's not true. That's not correct. It's easily converted to carbon. That's not correct either. It has a low heat of formation. That's not correct. That's not what we use as a fuel. Why we can really use ethanol as a good fuel, guys, is because it has a high heat of combustion. So this is our answer, right? And what this means in essence is that we're going to get a lot of energy given off, right? A lot of energy will be given off when we combust it, right? And because a lot of energy is given off when we combust it, then it's a very good fuel for us. We can use it to fuel different things, okay? So that's what makes it a good fuel, is because it has a high heat of combustion, okay? All right, so 40 is D. We are moving down to 41 now. So 41 says that unsaturated compounds, which are compounds that have what? Carbon, they can have carbon-carbon double bond, or they can even have triple bonds, right? Unsaturated compounds show addition reactions, but saturated compounds like a carbon-carbon single bond do not, right? They do not have addition reactions because why, right? Is it because saturated compounds contain double bonds? No, because saturated compounds actually contain single bonds. So this statement is not true at all. unsaturated compounds contain multiple bonds. That's true, and that is why they can do addition reactions, right? So the answer is B. And so remember now, when we have the carbon-carbon double bond, and that's an unsaturated compound, we can always add across this double bond to make it so that we have this kind of a situation. So if I had C2H4 was my original compound, right? And I reacted this with the bromine, I would just add the bromine across the double carbon-carbon double bond, and I'd end up with my H's are there from before, and I would just add a bromine here and add a bromine here, and then of course I'll still have my H's from before, right? So this particular property of them having multiple bonds is why we're able to do addition reactions with them, so we can add something across the double bond readily, okay? So this is our answer for B. This is not a correct statement. Unsaturated compounds contain carbon-carbon single bonds. That's not true. That's what saturated compounds have, right? And then this statement down here says saturated compounds are much more reactive than unsaturated compounds, and that's not true, right? Unsaturated compounds are going to be way more reactive, and that's simply because they have this carbon-carbon double bond, okay? So the only true statement here is that unsaturated compounds contain multiple bonds, and that's why we can do addition reactions with them, right? Because they have those multiple bonds in them. Okay? Okay, so moving down to 42 now. So 42 says that the diagram below shows some reaction, right? So this is kind of like a reaction scheme. So here we have ethene, right? And we subject ethene to steam, and then we're gonna get X, and then we can also get to X by fermenting glucose, right? So we ferment glucose, we get back to X, right? So first of all, let us say, what do we get from the fermentation of glucose? We're gonna get ethanol, right? That's how we form ethanol. That's one way of forming ethanol, is through the fermentation of glucose. So we're going this way. And then when we have ethene with steam, we can also get ethanol as well. And what we're doing in this particular step or this particular reaction is we are doing a hydration reaction, right? So this is a hydration step, and that's another way of producing X. So X in this case will be ethanol, right? So ethanol is our answer. So C is our answer for 42. Okay, guys? All right. So moving down to 43 now. What is the name of the following compound? So what kind of compound is this? Is what we have to get at right away, right? So we see that we have this C double bond O group. And so this is actually what we call an ester linkage, right? So this is an ester. This whole compound is an ester, right? And the ester is comprised of carboxylic acid. So the carboxylic acid portion would be all of this that I'm circling in blue, right? This is well, actually this part here. So let me erase that little part here. The part that's in blue, guys, is from the carboxylic acid, right? And then the part that's right here in red is from our alcohol, right? Now remember, esters are formed from the condensation of acid, and in this case, the acid is CH3COOH, and that is condensed with an alcohol. It undergoes a condensation reaction. So we're gonna have methanol in this case, CH3OH, right? And that's how we come up with this ester, right? So this part is from the acid, and then this part out here, the CH3O, is from the alcohol. So how we name them? The first part of the name comes from the alcohol. So the first part of the name is gonna be methyl, because the first part of the name comes from the alcohol. So the first part will be methyl, and the last part will come from the carboxylic acid, and this is ethanoic acid because there are 2 carbons in it. So this will be called methyl ethanoate. Let me put that in blue so you see that the ethanoate part is coming from the acid, right? All right, guys. So this will be methyl ethanoate because methylene is our alcohol and ethanoic acid is our acid that made this ester, okay? So that gives us C. So the answer for 43 is going to be C. Okay? All right. So moving right along to 44. 44 says, which of the following substances is a well-known polyamide? So polyamide is formed from the condensation of when you have an amine group, functional group, reacting with a acid functional group. Right? So it's a condensation reaction, and when we do that, we're gonna get something like a nylon. Right? So the answer for 44 is A. Plastics are not polyamides. Plastic are what? Polyethanes, right? Or polyalkenes are what plastics are made of. Bakelite is not it, and polystyrene is not it, right? It's actually nylon that's our polyamide, right? All right. So moving along to 45. 45 says, which of the following equations represents a condensation reaction? So here's that term again. A condensation reaction is a reaction in which you condense two functional groups to form a new functional group, and then in the process you get a side product as well, right? So you get a side product from a condensation reaction, right? So let's look at this one here and see. So A, what kind of reaction? We want to find a condensation reaction. That's our objective, right? So let's look at this first one and see what kind of reaction this is. So this looks to be what? This is C3H, what is this? It's C3H8, right? So that's an alkane, right? So that's an alkane, and that's an alkane reacting with bromine. And when that happens, what's actually happening is that this is a substitution reaction, right? So we know that when alkanes react with halogens, it's a substitution reaction, not a condensation, right? So this is not our answer that we're looking for. Let's look at the second one now. The second one is where we have an alkene, because you see this double bond. So this is an alkene reacting with HBr. Again, we're going to be able to add across that double bond, and that's exactly what we did. So this is an addition reaction, right, guys? Because it's an alkene, and we're adding across the double bond to come up with this haloalkene here, right? So this is an addition reaction for B, and so that's not correct. Remember, we're looking for a condensation reaction. So let's look at this one now. We have a carboxylic acid that's reacting with a base to form the salt of that acid and water. So we do get off water here, but this isn't what we would call a condensation reaction. This is just a metal reacting with an acid, right? So this is kind of what? This is kind of like a displacement kind of reaction. So this is not what we're looking for. For a condensation reaction now, this one where we have a carboxylic acid group and we have a alcohol group that's condensing together to form this ester group here and water, that's our that's our typical condensation reaction. So this is our answer. Okay, guys? So I just went through all of those to just show you that in the end, this one is the one that ended up being the condensation one, right? So just make sure you're comfortable identifying different types of reactions and coming up with what's condensation, what's addition, what's displacement, what's substitution, right? You should be comfortable with that, okay? So these are answers for 45. So moving down now to 46. 46 says, which of the following names is correct for the compound whose formula is H3C? So this is the condensed formula. H3C, CH2, CH2, CH2OH, right? So let's count the longest chain first of all. We're supposed to name this compound based on the condensed formula here. So this is our 1 carbon, 2 carbon, 3 carbon, 4 carbon. As a matter of fact, let me count that the other way, given that the functional group is right here. So we normally want it to be that our functional group is on the lowest carbon, right? So let me count from here. 1 carbon, 2 carbon, 3 carbon, 4 carbon, right? So if we have 4 carbons, right away that limit that we can narrow in on that being a bute of some sort, a butanol of some sort, really. Because it's an alcohol, because it has its functional group. It has 4 carbons, so we know it's a butanol, right? So we can strike out A and we can strike out C. So we're left with choosing between B and D, right? No, I said that the hydroxyl group, which is the functional group in an alcohol, is on the first carbon, so it's not going to be 2-butanol. That's only if the OH group was on the second carbon, which it's not. So we can strike out 2-butanol, and so we're left with N-butanol as our answer. Okay? So our answer for 46 is B. It's N-butanol. It just means that it's a regular straight chain butanol with the OH being on the very first carbon, okay? So 46 is B. So moving right along to 47 now. 47 says that the addition of hydrochloric acid to a solution of metallic nitrate gives a white precipitate, which is insoluble in water, right? But when you put it in aqueous ammonia, it becomes soluble, right? So let's think about this now. Metallic nitrate gives a white precipitate, it's insoluble in water. So let's see. So if we have HCl and a metallic nitrate, so let's just say XNO3, right? That's our metallic nitrate. And we react that with HCl, so we're gonna get an insoluble salt is what's gonna happen. So we're gonna get, we get HCl, right? So that's our insoluble salt, and we would also get HNO3 as well, right? So this is our insoluble salt, and they're saying that whenever we put this insoluble salt, XCl, where X is our unknown metal at the moment, when we react this, or when we put this in ammonia, aqueous ammonia, it then becomes soluble, right? So what are our chlorides that are insoluble? A chloride salt that's insoluble, it can either be a lead, of a lead metal, or it can be of a what's the other one? Silver, right? So they're telling us that we have nitrate, we react the nitrate with HCl, we're gonna get an insoluble salt. That's a chloride salt. So it can either be PB, so that would be what? It would be PbCl, it can be PbCl2, or it could be AgCl. Right? It's between these two because these two are the only insoluble chloride salts, right? No, it says that when we add soluble aqueous ammonia, it then becomes, when we add aqueous ammonia, it then becomes soluble, right? So this is the only one that becomes soluble when we add aqueous ammonia, and so our answer has to be that the identity of the metal X was silver. So what we started with was then what? Silver nitrate, okay? So our answer for 47 is A. Okay? So this question relies on your ability of knowing what would form when HCl reacts with nitrate, that you would have a displacement, first of all, where the X is going to displace the H and form HCl, and that this HCl that gets formed is going to be insoluble. So you're like, okay, what are my insoluble chlorides? It can either be PB or AG. Right, so it can be one of these two. Now, which of these chlorides are going to become soluble once you add aqueous ammonia? It's this one. So right away, we know that the identity of X was silver. And so then by extension, our entire nitrate, metallic nitrate, must have been silver nitrate, okay? All right, so that's 47. 47 is A. So let's go to 48 now. 48 says that a colorless gas, right, with a pungent odor turns blue litmus paper red. So right away we know that that's an acidic gas because it turns blue litmus red. And then it turns filter paper that's dipped in acidified potassium dichromate from orange to green. So it's actually going from Cr6 plus to Cr3 plus. So this gas is a good reducing agent, right? The gas is a good reducing agent because it's able to reduce the potassium dichromate. So that's all we know about the gas based on this little write-up here, okay? So they're asking us, what is the gas? Is the gas ammonia? No, it's not ammonia because ammonia is a basic gas and not an acidic gas. What's chlorine? Chlorine is actually an acidic gas, but it's not gonna have this kind of a reducing power. It's not a good reducing agent. It's more of an oxidizing agent, right? So we know that that's not going to be chlorine. Sulfur dioxide is an acidic gas, and it's also a very good reducing agent. So right away, we can stop at C, right? So the identity of our gas is sulfur dioxide, which is a good acidic, which is an acidic gas, and it's a good reducing agent, okay? All right. So now we move on to question 49. So 49 says, so this says item 49 to 51 refer to the extraction of aluminum from bauxite by electrolysis. Okay, so that's a process that we have to be familiar with per our syllabus, right? So the extraction of aluminum, it's extracted by electrolysis, right? So they told us that up here. So now they're asking us some specifics about the process, right? So cryolite is important in the extraction in the extraction process because what does it do? Like, what is the importance of cryolite, right? So cryolite, let me tell you what cryolite does. So the aluminum, right? So the bauxite ore is Al2O3, right? And so that Al2O3, that bauxite has a very high melting point, right? Of about, say, 240 degrees C, right? No, it's very difficult and it's expensive to like keep this aluminum oxide in a molten state so that we can have electrolysis. Because remember, this has to be molten for electrolysis, but it's hard to do that because the melting point is so high, right? So what the cryolite does now, or what they do in practice, is that they add some cryolite to this mixture. And what the cryolite does is it's gonna cause a drop in the melting point, right? So then it's easier to get that molten Al2O3 that we can then use in electrolysis, right? So we add cryolite to the Al2O3 so that we get a drop in the melting point of Al2O3 or bauxite, and that drops to 900 degrees C. So this is definitely more manageable, right? To make molten Al2O3 coming from this point, right? So the answer here is going to be D, right? We add cryolite. It's important to add cryolite because it lowers the melting point of the electrolyte, which is Al2O3, and so it makes the process more feasible, okay? All right. So 50 now says during electrolysis, the carbon anode tends to, what happens at the carbon anode when we're electrolyzing bauxite, so Al2O3? At the carbon anode, right? We know that anions are going to go towards the anode, right? So in Al2O3, which is our electrolyte, our anion is what? It's the oxygen, right? So what's going to happen is we're going to have O2 minus. Then this is going to go towards the anode because this is our anion, right? And anions go towards the anode. So this anion is going to go towards the anode and it's going to get oxidized because oxidation takes place at the anode, and we're going to end up with oxygen gas, right? Just that neutral oxygen gas is what's going to happen at the anode, right? So that's what we're going to get. Oxidation. Oxidation is a loss of electrons. And so, yeah, so this oxygen is going to lose these 2 electrons and it's going to end up being O2 neutral, right? So that's our half equation there for that process. So that's our half equation there. And of course, if I were to balance it, I'll put a 2 here, right? So this is our half equation at the anode, right? So at the anode, this oxygen gas is liberated, right? So what's happening now in terms of what happens at the anode after that oxygen gas is formed is that oxygen gas, that hot oxygen gas that comes off, is gonna react with the graphite anode or the carbon anode. So we're gonna have that carbon anode reacting with the oxygen and we're gonna get carbon dioxide, right? So we're gonna get CO2 forming at that point. What happened? Yeah, so we're gonna get carbon dioxide gas, right? And so because of that now, so it says that the anode is gonna be oxidized by oxygen. So that matches this one here, right? So the anode we're gonna get oxygen, and the oxygen is gonna oxidize the anode. Okay, so the anode is gonna be oxidized by oxygen. Okay, all right. So 50 is B. So 51 now says that which of the following materials is used for the cathode? So in this process of electrolysis of bauxite, we're gonna use both the cathode and the anode as carbon. So it's a carbon cathode and it's also a carbon anode. Okay, they're both made of carbon. So our answer here is B. Okay, so 51 is B. So moving down to 52 now. 52 says that a white metallic hydroxide, X, undergoes no color change when heated, right? So it's pretty much stable, a stable metallic hydroxide. However, it dissolves in both dilute sulfuric acid and sodium hydroxide solution. So what is this metallic hydroxide, right? It dissolves in both sulfuric acid and sodium hydroxide, so that means that it's an amphoteric hydroxide. It has both properties. It has acidic properties and basic properties, and so we're looking for an amphoteric hydroxide among our answers, right? To be identified as the metallic hydroxide in this case, right? It reacts with both acid and bases, so it's an amphoteric hydroxide. Now, our only amphoteric hydroxide among the choices is gonna be aluminium hydroxide, right? Yeah, so that's our only amphoteric hydroxide here is aluminium hydroxide, and so that's our answer for 52. Okay? All right, so moving along to 53 now. So 53 says, which of the following elements is most electropositive? So electropositive means that the element is going to readily lose an electron to become positively charged, right? And that's going to be our most reactive. The most reactive metal given among all of these is the one that will be most excited to give away, right? Its electrons and then become positively charged. So it's the most reactive one out of all of these, right? And so this, we can use the reactivity series to figure out which of these is the most reactive one. And so when we do that, let's write our reactivity series here. So we have zinc, calcium, aluminum, and magnesium here, right? So out of all of these, calcium is gonna be more reactive than magnesium, which is gonna be more reactive than aluminum, which is gonna then be more reactive than zinc. Okay? So calcium is the most reactive, then magnesium, then aluminum, then zinc. So our calcium is going to be the most electropositive. Remember, our most reactive metal, based on the reactivity series, is the one that's going to be the most electropositive. It's going to be the most excited and ready and willing to give up its electrons to become positively charged. Okay? So that's calcium in this case. So our answer for 53 is B. Okay? So 54 now says that to positively identify sulfur dioxide gas, a strip of paper is soaked in an aqueous solution of what? All right. So this is the key word here. The key word is to positively identify, right? In the very first instant, we can be like, okay, sulfur dioxide is an acidic gas. Like we know it's an acidic gas. So we know that if we use a blue litmus paper, it's gonna turn red, right? But that's true for other kinds of gases that are acidic in nature. So carbon dioxide is an acidic gas, it would give you that same result. Nitrogen dioxide is an acidic gas, it would give you that same result where we turn blue litmus red. So this can't be used to positively say, absolutely positively, I know that it's sulfur dioxide. You can't use this. You can't use that because there are other gases that give that same result, right? Iron sulfate, what's gonna happen in that case? So we can't really use iron sulfate because so sulfur dioxide is a powerful reducing agent, we said, right? So what would it reduce the iron to? We wouldn't really see a color change here that we could say, okay, positive, that is sulfur dioxide, right? So we wouldn't really use that. Lead ethanoate, that's an ester, salt of an ester. Can't really use this either, right? What we can use and be positive and confident in our result that this is in fact sulfur dioxide is potassium dichromate, right? And what's gonna happen is that, as we said, sulfur dioxide is not only an acidic gas, it's also a good reducing agent. We would have said, we said this earlier, right? It's also a very good reducing agent, right? And so if we use potassium dichromate and we see that it goes from that orange color that it typically is when it's in the 6+ state, and then that changes, if that changes to green, then we can be like, okay, definitely or gas is a strong reducing agent. It reduced my dichromate from 6+ to green 3+. So then you can be like, okay, for sure, this has to be sulfur dioxide, okay? So remember, when we're positively identifying something, we want a test that will say definitively that this is for sure sulfur dioxide. And this particular solution can tell us that, because sulfur dioxide is going to reduce it, and then we'll know for sure that that was in fact sulfur dioxide that we have, right? So moving along to 55. 55 says, which of the following substances can cause temporary hardness of water? Okay, so temporary hardness of water is related to two species, right? It can be magnesium hydrogen carbonate, and it can also be as a result of calcium hydrogen carbonate, right? These are the groups that contribute to temporary hardness of water. So that Mg2+ ion and that calcium 2+ ion, those two ions, particularly in the hydrogen carbonate state, are what's going to cause temporary hardness. And temporary hardness means that if we boil that water, we can get rid of that hardness, okay? And these are the species that are responsible for that temporary hardness. So we look among our answers. It's not calcium carbonate. It's not magnesium carbonate. It's calcium hydrogen carbonate, not sodium hydrogen carbonate. So those are all wrong. So among our selection, the only one of these that are present is calcium hydrogen carbonate. So that's our answer, okay? So 55 is C. All right, so 56 now. 56 says, which of the following reactions is likely to take place most readily, right? So again, when we see these reactions that involve all these different metals, right away, we have to pull for our reactivity series, right? Because our reactivity series is going to tell us out of all of these metals. So we have zinc and we have a nitrate of another metal that's in that same reactivity series. So if we have zinc, which one of these is going to take place most readily? So which one of these metals are furthest away from zinc, assuming that zinc is above it, right? So this is our reactivity series, right? So we have potassium, calcium, magnesium, aluminum, carbon, zinc, iron, lead, hydrogen, copper, and silver. So this is our reactivity series, and the ones that are at the top are the more reactive ones. So these ones, the ones that are further up top, will displace any metal that's below them in a salt, right? From the salt that it's in. So zinc, let's look at this first one. Zinc is above lead, right? So zinc is here, and then lead is here. So it could displace it, but they're fairly close to each other, even though zinc is above it. So it could work, right? But which one is going to be happening most readily? Because that's what they're asking us. We want to find one that's like super far away from zinc and below it, right? Because if it's below zinc, zinc can displace it. Now, if it's super far away from zinc, we know that zinc is going to be far more reactive when compared to that one, right? So if there's a silver is at the bottom and zinc is up here. So I would say that the one that has silver in it that reaction would happen most readily. So that's D. Okay? So we're looking at the position of zinc in relation to these other metals that it's trying to displace from the salt. And because zinc is up here and silver is all the way down here, it's gonna displace silver from its salt and form zinc nitrate, and you're gonna get that silver metal free. Okay? So 56 is our answer here. And again, just make sure you're comfortable with the reactivity series, where different metals are, and what the actual reactivity series mean. And what the reactivity series means is that whatever is up closer to the top is going to be more reactive. Okay? All right. So let's look at 57 now. Items 57 to 58 refer to the following diagrams, which illustrate 4 methods of collecting gases. So there are 4 methods of collecting gases that are shown here. We have A, we have B, we have C, and we have D, right? They're saying that through the diagram A, B, C, or D, which corresponds to each item, each diagram may be used once, more than once, or not at all, right? So in this first case, we have a downward delivery. This case, we have an upward delivery. right? Or a downward displacement of air. And this one is going to be an upward displacement of air. And then this one is going to be a downward displacement of water, right? And then this one we have, what is this one? This is a downward displacement of concentrated sulfuric acid. Okay? So which of the following methods is suitable for collecting moist oxygen? All right, so when we're collecting moist oxygen, we're going to want to use something that has water in it. So right away, we're zeroing on C for our answer here because the oxygen is slightly soluble in water, so we can get that separation that we need. We'll be able to separate the oxygen from the water. But even what's most important, right, is that the oxygen is less dense than water. And so the oxygen will flow up in this region and we'll be able to get our oxygen up here and the water will stay down here, okay? So we'll use C in this case for 57 to collect oxygen. So oxygen is collected by the downward displacement of water, and that's because oxygen is less dense than water. So we collect the oxygen up here, okay, in the gas jar. All right. So as it relates to carbon dioxide now, carbon dioxide is more dense than air, right? Carbon dioxide is more dense than air. So what's going to happen is that when compared to air, because it's more dense, it's going to fall to the bottom of our jar. And so we collect it using downward delivery. All right, so we're going to collect it using downward delivery. And this is what shows a downward delivery setup, where we're going to get our carbon dioxide inside of it. And we're going to have an upward displacement of air. Since the carbon dioxide is more dense than the air is going to go up here, right? And the carbon dioxide is going to go down. So we say that we collect that carbon dioxide by downward delivery, right? So that's downward delivery. That's how the carbon dioxide is going to be delivered downward, and then the air is displaced upward, okay? All right. So that is, what's that? That's going to be A, right? So our answer for 58 is A. That's downward delivery because the CO2 is more dense. It's going to fall down to the bottom and the air is going to go up, right? So A is 58. Okay? All right. So moving along now to 59. 59 says, it's item 59 to 60 refer to the following information, right? So this is a qualitative analysis kind of a thing now. So we have a solution of iron sulfate and we add that until it's in excess to a solution of barium nitrate. And then the precipitate produced is filtered off. So we're going to filter off our precipitate, add water to the residue and wash it, right? So we add water to the residue that's in our filter paper and wash it, right? So what's that precipitate, the color of that precipitate gonna be, right? So let's look at the equation that describes what's actually happening, right? So we have iron 2 sulfate, and that's reacting with barium nitrate. And from that, we're going to get that the iron is going to displace the barium. And so we're going to end up with FeNO3, 2, and then BaSO4. So we're going to get barium sulfate, right? Now you might remember that barium sulfate is an insoluble sulfate, and it actually forms a white precipitate, right? So this is a white precipitate that gets formed here. And of course, this is a nitrate, so it's going to be soluble. So that's not going to form a precipitate at all. So the precipitate that's formed is actually that of barium sulfate, and that is a white precipitate. So our answer for 59 is B. Okay? All right. So if the barium sulfate is our precipitate, that means that our filtrate was the iron nitrate, iron 2 nitrate. Okay? So 60 says, with which of the following solutions would the filtrate produce a precipitate? So this is our filtrate, right? So when the filtrate reacts with which one of these, will it form a precipitate? No. It's important to remember that when we have precipitate forming, it means that we're forming an insoluble salt, right? Whenever we have a precipitate, it means that an insoluble salt is formed, right? So when iron nitrate reacts with which one of these, will it form an insoluble salt? Is essentially what this question is asking us, right? So here we have our iron nitrate reacting with barium chloride. When that happens, the iron is going to displace the barium and we're going to get FeCl2 being formed and barium nitrate. No, iron chloride is soluble, so that's not going to be a precipitate because that's soluble. Barium nitrate is a nitrate and all nitrates are soluble, so this is going to be soluble as well. So in this first case, we're not going to get a precipitate. We're going to get soluble salts, okay? Now in the second case, so this is case 1 and this is case 2. So in case 2 now, we have iron nitrate reacting with ammonia. And when that happens, what's going to happen is that we're going to get an ammonium salt. So we're going to get ammonium nitrate as our salt. And remember, all nitrates are soluble. So this will be soluble. Ammonium nitrate will be soluble. But then we get this hydroxide that's going to form. Because it's aqueous ammonia, we're going to have some water in that mix. And so that water is going to combine with our iron. And we're going to get iron hydroxide, right? No. Remember, all hydroxides are insoluble. All hydroxides are insoluble except if it's like the hydroxide of potassium or an ammonium ion or sodium, right? But other than that, all of our hydroxides will be insoluble. So this is insoluble that forms here. So from 2, we're going to get an insoluble iron hydroxide. And so this would form a precipitate, right? So in the third case now, we have, again, the iron nitrate reacting with sodium hydroxide, right? And when that happens, the iron is going to come in and displace the sodium, and we're going to end up getting iron hydroxide again, which we just said above is insoluble. So that's going to be a precipitate, right? That's going to form a precipitate. And then we're going to get sodium nitrate as well. But we know that nitrates are soluble, so that's not going to give a precipitate, okay? But this product is going to form an insoluble precipitate because hydroxides, as we said, are insoluble. So these two last ones are going to give us a precipitate. And so our answer here for 60 is going to be 2 and 3. It's going to be 2 and 3 only. So that's going to be C. Okay? So 60 is C. So with that, we have come to the end of our specimen paper, or paper 1 that CSEC provided us with. I hope that this was helpful for you. Wishing you nothing but the best in your exam. And please remember to like this video, share it with your friend, comment down below if it was helpful, subscribe to the channel, and I'll see you in the next video.